Namaskar. Today let us discuss multiplexers, demultiplexers, encoders and decoders. Multiplexers, demultiplexers, encoders and decoders. These are some of the combinational circuits. Combinational circuit is one, its output depends only on current inputs. Let us see this. Decoder, encoder, multiplexer and demultiplexers are some of the combinational circuits. Combinational circuit output depends only on the current inputs. Simplest combinational circuits are our gates like AND gate, OR gate, exclusive OR gate and so on, as shown in this figure. These are the simple combinational circuits. These gates output depends on purely current inputs. Now, decoder function is, it converts binary information from n input lines to a maximum of 2 power n unique output lines, and encoder performs an inverse operation of decoder. It has 2 power n or fewer input lines and n output lines. The output lines generate the binary code corresponding to the input value. Next, multiplexer selects binary information from one of many input lines and directs it to a single output line. Demultiplexer performs an inverse operation of multiplexer. Now, let us start with decoder first. The pseudo block diagram of decoder looks like this. It has inputs and outputs. It also has enable inputs. Enable inputs must be activated to get valid output. The job of decoder is to convert this input code word into output code word. In the decoder, binary n2 2 power n decoder. A binary decoder has n inputs and 2 power n outputs. Only one output is active at any point of time corresponding to the input value. Now, we see the block diagram of n to 2 power n decoder. It has, as shown in this figure, it has n inputs and 2 power n outputs. If n value is 1, then it becomes 1 to 2 decoder. If n is 2, it is called 2 to 4 decoder. If n is 3, it is called 3 to 8 decoder and so on. Now, the simplest binary decoder is 2 to 4 binary decoder. Its symbol as shown here. It has 2 inputs x and y and 4 outputs f0, f1, f2 and f3. As the input changes, one of these outputs will be 1 and other outputs will be 0. At a given time, only one output will be high. We can see this from the truth table. If x, y are 0 and 0, then f0 will be 1 and other outputs f1, f2 and f3 are zeros. If x is 0 and y is 1, then f1 will be 1 and other outputs are at 0. If x and y are 1 and 0, then f2 will be 1 and other outputs are zeros. Lastly, if x and y are both 1s, then last output, that is f3, will be 1 and other outputs will remain at 0. Now, we see the circuit diagram of 2 to 4 binary decoder. In this figure we can see these are inputs to the decoder and F0 to F3 are outputs. Inside the circuit, first XY are inverted to get X bar and Y bar signals, and X bar and Y bar signals are used as inputs to these AND gates. AND gate is the basic decoding element, because if its inputs are high, then only its output will be high. That is, AND gate output will be high if and only if all its inputs are high. If at least one of its input is 0, then AND gate output becomes 0. Now we can see from these four, the first AND gate has inputs X bar and Y bar, second AND gate has inputs X bar and Y, third AND gate has X and Y bar as inputs, and last fourth AND gate has X and Y as inputs. When X and Y both are 0, you can see X bar and Y bar, they become 1, and since these two are connected to first AND gate, it will be 1. And for other AND gates, at least one input is 0, so their outputs are forced to 0, as shown in the first entry of the truth table. Now we see what happens if X is 0 and Y is 1. So for this combination, we can see second AND gate inputs are high, hence its output will be high, and for other AND gates at least one input is 0, so their outputs are forced to 0. Hence for 0 1 input combination, the output will be 0 1 0 0. Now we see what happens if X equal to 1 and Y equal to 0. Here the third AND gate now has high inputs, both high inputs, hence its output will be 1, and for other AND gates the outputs are forced to 0, because for them at least one of the inputs are zeros. And last possible combination is 1 1. If X equal to 1 and Y equal to 1, the last output, that is F3, will become 1. Let us see from this diagram. See, F3 has now all 1 inputs and its output is 1, and for other AND gates output is forced to 0, because at least one of the input is 0 for them, and these are all called active high output for this F3, because here we have used AND gates. AND gate output will be high, and we can also use NAND gates to design decoder. If we use NAND gates, the active output will be low and inactive outputs will remain at high, that we see in the next diagram. So this is 2 to 4 binary decoder active low output circuit. Here you can see instead of AND gates we use NAND gates, hence the outputs are inverted. If you see the truth table, at a given time one of the output will be 0 and other outputs will remain at high. For 0 0 combination, F0 will be 0, for 0 1 combination F1 will be 0, for 1 0 combination of inputs F2 will be 0, and for 1 1 combination of inputs the last output F3 will be 0. This we see on circuit diagram on the board. This is 2 to 4 decoder 74155. It has one enable pin. Enable pin must be activated so that the outputs are valid, and these are two inputs X and Y, or lower order bit is A0, higher order bit is A1, and these are the outputs Q0, Q1, Q2 and Q3. We observe whether the output is 0 or 1 by connecting these two LED driver. If output is 1, LED will glow. If output is 0, LED will be off. Now I connect inputs, this A0, okay, A1 to this group, high and low group, and for A0, lower order bit, I am using black color, this bit. And now to check the outputs, I have to connect these outputs to LEDs. Now you see I am giving some input, in this case 0 0, but all are becoming high because I have not enabled the IC, because here you can see this is active low enable. I should connect this to low. Now you can see for 0 0 input, that is A0 is 0 and A1 is 0. So the first output, that is Q0, is becoming 0 because it is active low. And now we see if A0 is 1 and A1 is 0, that is 0 1 combination. Now you can see second LED is switched off, that is this second output is activated. And for 1 0 combination, this is 1 0 input and the third output of decoder is going low, that is it is getting activated. And similarly the last combination, that is 1 1 inputs, both X and Y are high. Now last LED is going low, indicating last output is activated. This is how we can make use of decoders. Now we see, now so far we have seen 2 to 4 decoder, 2 to 4 decoder. Now we see 3 to 8 decoder. 3 to 8 decoder has 3 input lines and 8 output lines. At a given time, one of the output of 3 to 8 decoder will be activated. If it is active high, the output will be high and rest of the outputs will be at 0. Now we see it in truth table. As shown in this truth table, since there are 3 inputs, all possible combinations are 2 cube, that is 8. So for first combination 0 0 0, F0, that is the first output, is going high and other outputs are remaining at 0. And for second combination, X is 0, Y is 0 and Z is 1, that is 0 0 1 input, F1 will high and other outputs will remain at 0. For third combination 0 1 0, F2 will be high and other outputs remain at 0. And fourth combination, where X is 0, Y is 1 and Z is 1, F3 will remain high and other outputs will be 0. And next combination 1 0 0, fourth output will be high and other outputs will be 0. For fifth combination, that is 1 0 1, F5 will be high and other outputs will be 0. And for 1 1 0 combination, F6 will be high and other outputs will be 0. And last possible combination is 1 1 1. For this last output, F7 will be high and all other outputs will remain at 0. Now let us see the circuit diagram for 3 to 8 decoder. Here you can see X, Y, Z are inputs, F0 to F7 are outputs. X, Y, Z these are inverted and total x, x bar, y, y bar, z, z bar, these 6 signals are used as inputs to these AND gates. First AND gate, if we see which output is F0, it has 3 inputs, 3 inverted inputs. This is x, x bar, because x is inverted, x bar, and other one is y bar, other one is z bar. Hence F0 is given as x bar dot y bar dot z bar. So this output will be high if and only if x is 0, y is 0, z is 0, because x bar will become 1, y bar will become 1, z bar 2 will become 1. Hence for the inputs 0, 0, 0, the first AND gate will be activated. Whereas for other AND gates, you can see at least one of the inputs will be 0, hence they will be forced to 0. You see second AND gate, its output is x1, x bar, y bar and z. And since for 0, 0, 0 input, since z is 0 and since this is input to the second AND gate, its output will be forced to 0. Like this, we can apply the logic for all remaining outputs and we can check out. Next, so far we have seen decoders, 2 to 4 decoder, 3 to 8 decoder. Now we see encoders. Encoder is a circuit which acts as inverse of decoder. Now an encoder is combinational circuit that performs the inverse operation of a decoder. Example, 2 power n to n decoder and 2 power n to n encoder and priority encoder. Here we can see it has 2 power n inputs and n outputs. One of the input will be activated and its code will be made available at the output of encoder. So that we see the simplest encoder is a 2 power n to n binary encoder, where it has only one of 2 power n inputs high, that is equal to 1, and the output is the n bit binary number corresponding to the active input. Now we see the general representation of encoder, binary encoder. It has 2 power n inputs and n outputs. If in inputs only one should be activated and its corresponding code will be displayed or generated at outputs. Now we see simple encoder, that is 4 to 2 encoder. It is inverse of 2 to 4 decoder. This 4 to 2 encoder has 4 inputs and 2 outputs. The circuit diagram for 4 to 2 encoder is like this. It got 4 inputs and 2 outputs. Here you can see I0 is not connected at all to any of the components. I1 is connected to first OR gate and I2 is connected to second OR gate, whereas I3 is connected to both the OR gates. As a result, it functions like this. If I0 is 1 and I1, I2, I3 are 0 as per the first entry of this truth table, then the outputs will be affected by these 3 inputs I1, I2, I3. Since all of them are 0, all these 2 OR gates outputs will be 0, because you know OR gate output will be high if and only if at least one input of the OR gate is high, or in other words OR gate output will be 0 if and only if all its inputs are zeros. Now we see the second entry of the truth table, where inputs are I3 is 0, I2 is 0, I1 is 1 and I0 is 0. That is, I am making I1 high. all other inputs are zeros. Now here you can see, since the first OR gate input is now high, its output is high, that is O0 is 1, and whereas for second OR gate it got I2 and I3 as inputs, and since I2 and I3 are zeros, I2 and I3 are zeros, the second OR gate output will be 0, hence the output code will be 0 1. And next, if I2 goes high, then by applying same logic we can see output of this OR gate, second OR gate, that is O1 will be high, and first OR gate output is 0, hence the output code is 1 0. And for third input, if it goes high and all others are at 0, then since I3 is connected to both the OR gates and since it is high now, both outputs will go high, hence generating 1 1. So this is how 4 to 1 encoder works, but this simple circuit has drawback, that is, in the absence of inputs also it generates some code, that is in this case 0 0. To overcome that, we introduce another output signal called input active control signal, and that can be generated simply by using 4 input OR gate. We take 4 inputs of the encoder and connect them to OR gate, and we observe the output of OR gate. Now when in the absence of all inputs, that is when I1 to I0 to I3 inputs are 0, the output of OR gate will be 0. When this input active control signal is 0, the output code present at the output of this encoder is invalid. We see that in the next slide. Here you see, except this OR gate, the other circuitry is similar to the previous circuit diagram, and this is 4 input OR gate, and all I0, I1, I2 and I3 are connected as inputs to this OR gate, and its output is called input active control signal. If this is 0, the output of encoder is invalid, and when one of the inputs are high, then OR gate output will be high, hence the code present at encoder output will be valid. Now we see 8 to 3 encoder. It is very similar to or inverse. It is inverse of 3 to 8 decoder. It is also called octal to binary encoder. Octal to binary take 8 inputs and provides 3 outputs, thus doing opposite to 3 to 8 decoder. At any one time, only one input line has value of 1. Now we see the truth table for this. See, it has I0 to I7 inputs, total 8 inputs and 3 outputs. If I0 is 1, the code generated will be all zeros. If I1 is 1, code generated will be 0 0 1. For I2, 0 1 0. For I3, 0 1 1. For I4, 1 0 0. For I5, 1 0 1. And for I6 input, that is when I6 goes high and other inputs are at 0, then the output code generated will be 1 1 0. And lastly, if I7 goes high, then the code generated will be 1 1 1. Now we see the circuit diagram for this. Based on the truth table, we can draw the circuit as shown in this diagram. Here Y0 is generated by observing I1, I3, I5 and I7. Y0 bit will be high if one of these inputs are high. Y1 will be generated by using I2, I3, I6 and I7 inputs, because if at least one of these goes high, Y1 will become high. Only one input has to be high. Now Y2 output is has inputs I4, I5, I6 and I7. If one of these becomes high, Y2 will become high. This circuit can be designed by using truth table that we have seen in the previous slide. So far we have seen 4 to 2 encoder and 8 to 3 encoders. Now we see multiplexers. A multiplexer, simply it is called MUX, is a digital switch which connects data from one of n sources to the output. That is, it has n inputs and one output. Only one input from the available n input will be selected and will be connected to the output. For this we need to use selection lines. Based on the selection line input that to be connected from given inputs to the output will be decided. A number of select inputs determine which data source is connected to the output. Now we see the block diagram of multiplexer. It has one enable input. This should be activated so that the output is valid, and you can see n data sources and one data output. One of these input data has to be connected to the output data. Which one has to be connected to the output? That depends on the code present at select lines. Mechanical equivalent of multiplexer. This is a rotary switch can contact with any of the inputs and which is connected to the output, and at any given point of time only one input gets transferred to output. That is very clear from this diagram. Now first input is connected to the output. When the switch rotates to this place, second input will be connected. Only one input will be connected to the output at a time. Now simplest of multiplexer is 2 to 1 multiplexer. It has two inputs A and B, one selection line. If S equal to 0, then A will be connected to output, that is Y becomes A, and if S equal to 1, then B will be connected to output, that is Y becomes B, as shown in this truth table. Next we see 4 to 1 multiplexer. 4 to 1 multiplexer has 4 inputs and one output. One of these 4 inputs will be selected and connected to the output based on these selection inputs. Now we see the circuit diagram. Here you can see except I0, I1, I2, I3 inputs and this OR gate, rest of the circuit looks like decoder. It is actually a decoder, 2 to 4 decoder. Already we have seen one of the output of decoder will be high at a given time, and if for example this first AND gate is enabled because its two inputs are high, so its output depends on the third input I0. If I0 is 0, the output of this AND gate will be 0. If I0 is 1, the output of this AND gate will become 1, and all these outputs are connected to the output of multiplexer through multi-input OR gate, in this case 4-input OR gate. And since only one of the output is high, other outputs of the decoders will be 0 for this decoder. Only one output of decoder controls the output of whole multiplexer. Now we see for the first combination, that is when selection lines are 0 and 0, I0 is connected to the output because first AND gate has two high inputs, so its output depends on the input, actual input of the multiplexer. Whereas for other AND gates, since at least one of the input is 0, their outputs are forced to 0, so they won't affect the output of the multiplexer. Now we see next combination 0 1. When inputs are, that is when the selection lines are 0 1, then second AND gate inputs, selection inputs are high, hence its output depends on I1 as shown in this truth table. You can see this input from I1 to output, this path is sensitized, that is the output of the multiplexer depends only on this input, other AND gates outputs are forced to 0. And third combination we can see 1 0, for 1 0 third AND gate output path is sensitized, that is its input and output are connected, and output of the multiplexer follows I2. And similarly for 1 1 combination, last AND gate is enabled, or the output of this last AND gate path is sensitized, so the output of the multiplexer follows I3 only. And we can also construct large multiplexers. Larger multiplexers can be constructed from smaller ones, and 8 to 1 multiplexer can be constructed from smaller multiplexers that we see. Now we see 8 to 1 multiplexer. This is constructed by using 2 4 to 1 multiplexers and 1 2 to 1 multiplexer. In the first layer we have 4 to 1 multiplexers, in the second layer we have 2 to 1 multiplexer. And since 8 inputs, we need to have 3 selection lines, S0, S1 and S2. Now for example, for the first combination S2, S1, S0 are zeros, that is S0, S1 is 0 as well as S2 is also 0. Since S0, S1 is 0, I0 will be connected to the output of first layer multiplexer, and that is input to the second layer multiplexer. And since second layer 2 to 1 multiplexer has 0 selection input, the first line will be connected to the output. Hence for 0 0 0 selection lines, I0 will be connected to output of the multiplexer. This same logic we can apply for all other inputs. Now we see demultiplexers. Demultiplexer connects data from one input source to one of n outputs, usually implemented by using n to 2 power n binary decoders, where the decoder's enable line is used for data input of the demultiplexer. The block diagram of demultiplexer looks like this. It has one input and n output. The one input, that is input, data input, will be connected to one of these outputs depending on the selection bits present. The mechanical equivalent of demultiplexer looks like this. This is a rotary switch, can contact with any of the outputs and which is connected to the input. At any given point of time, only one output gets connected to the input. You can see here this input switch will be connected at a time to only one of the outputs. Now it is connected to the first output. Okay, if I present proper selection line code, it may be connected to this third output and so on. Now we see 1 to 4 output multiplexer. This has one input and 4 outputs, and it needs to have 2 selection lines, and its symbol is 1 to 4 demultiplexer symbol is this, 1 data input and 4 outputs. Selection lines are S0 and S1. If S1 and S0 both are zeros, then data will be connected to first output, that is F0, that is F0 equals to D, and other outputs will remain at 0. For 0 1 selection lines, F1, that is second output line, will be connected to the input line, that is F1 will become D. For 1 0 combination, F2 will become D, and lastly for 1 1 combination, F3 will become D. Now we see the circuit diagram of 1 to 4 demultiplexer circuit. You can see this is, except this green line, the rest of the circuit is simply a decoder, and this data input line is connected to all output AND gates. And you know, based on X and Y, one of these AND gates will be selected, that is, one of these AND gates output will be high. And since we have third input now, it also depends on the value of third input. Say for example, X, Y, when both are zeros, you know, first AND gate will be selected, and other AND gates, they are forced to 0, that we have already seen. Now first AND gate, since it is also having this data input, if data input is 0, F0 will become 0. If data input is 1, now AND gate output, that is first AND gate output, will become 1. That is, simply F0 is following data input. Hence in the truth table it is shown like this: F0 will be D for XY 0 0 combination. Similarly for 0 1 combination, F1 output follows the input data line D. For 1 0 combination, F2 follows D, and for 1 1 combination, F3 follows the data input. Now we see this idea can be extended to 1 to 8 demultiplexer. As shown in this slide, we see it got 3 selection inputs and 8 outputs F0 to F7 and 1 data input in white color. Okay, it is connected to all AND gates as input. We have already seen one of these AND gates output will be high at given time, and say for example F0 AND gate, this is high for 0 0 0 input, this AND gate output will be high, and since it has fourth input as data input, if data input is 0, this AND gate output will become 0. If data input is 1, this AND gate output will become 1. Like this, same logic can be applied for other outputs of 1 to 8 demultiplexer. So constructing demultiplexer is simple. It is actually using decoder only. Now we summarize whatever that we have seen so far. First we saw decoders. A binary decoder has n inputs and 2 power n outputs. Only one output is active at any point of time corresponding to the input value. That is, decoder has, this is binary decoder, it has n inputs and 2 power n outputs. One of the output from this 2 power n will become activated. If it is active high, that particular line will become 1. If that is active low, it will become 0 based on the input code present. We have seen 2 to 4 decoder, 3 to 8 decoder. Next we have seen encoders. Encoder, simply it performs inverse function of decoder. Encoder performs an inverse operation of decoder. It has 2 power n input lines and n output lines. The output lines generate the binary code corresponding to the input value. And we also have seen multiplexers. Multiplexer selects binary information from one of many input lines and directs it to a single output line. That is, we have seen 4 to 2 multiplexer, we also have seen 4 to 1 multiplexer, we have seen 8 to 1 multiplexer. This is basically selects one of the input by using decoding logic and connects it to the output line. And lastly, we have seen demultiplexer. Demultiplexer is very similar to decoder, that is enable input of decoder. If it is used as data input line, then that same decoder can be called as demultiplexer. It has one input line and n outputs. One of the output line will be selected and data input that will be connected to the output line based on the selection inputs. So these are some of the combinational circuits: multiplexer, demultiplexer, encoder and decoder. The remaining topics we will see in the next session.